Hello, fellow problem solvers. So today we're going to be doing a problem from the Iranian team selection test from 2009, day 1, problem number 2. This is a phenomenal number theory problem. Just the right difficulty if you want to try, if you're feeling intermediate in your number theory problem solving skills, then try out this problem to level up. And I suggest you take a minimum of 20 minutes, ideally 45 to an hour, but not more than 2 hours on this problem. If on the other hand you'd like to go along with us, I suggest you take a preliminary look for the next 10 minutes. So without further ado, let's begin. So we have this sequence, like a is a fixed natural number, and we must prove that the set of prime divisors of an for every single n is infinite. So the way I like these types of problems, and the way I like to just start them off, is by assuming the contrary, because prove that something has an infinite number of prime divisors, assume there's a finite number of primes dividing the terms of the sequence ai for I from 1 to infinity, and then let's assume okay, p1, p2 till pk are all the primes that divide some members of the sequence. Let's assume these are all there are. Now, does this give us anything at the beginning? Well, no. We still need to look at the problem and figure out what we can do. And one thing, when there's only finitely many primes, that means that you will have m and n such that a prime divides both of these. Like pi, one of the pi's divide this and this for some m. For some m and n. If we just take the first k plus 1 members of the sequence, then we will be forced to find two which are divisible by the same prime. And let's see what needs to hold. So the first thing I would do is just subtract. So I get rid of a. And now I have 2 to the 2 to the m minus 2 to the 2n is divisible by p. Now here, I would actually invite you to pause for another 5 to 10 minutes and play around with the problem, see if you can push it forward and maybe solve it, maybe get an idea. And before I continue on with the next sort of step, I just want to point out a misconception that some people might have when trying to solve this. You might think because these get super big that you just have to get more primes involved, but that's not the case. The sequence an is equal to 2 to the 2 to the n gets incredibly big, as large as you want it, but the set of its prime divisors is just 2. So there is no immediate size argument that you can make. So now let's look at this. Okay, so this means assume n is less than m, get it out, 2 to the n, m minus 2 to the n, minus 1. We have this. Now let's also assume this isn't a power of 2. We can basically assume that this isn't going to be equal to a power of 2 for a large enough m, like starting from a large enough m, and this is not going to be a power of 2. So there are some other odd prime divisors, and the reason I assume this is to just get rid of this. And now we're left with p divides 2 to the 2 n minus 2 to the n minus 1, which means n is congruent to 1 modulo p. And now here's where some technique gets involved. We know that 2 to the p minus 1 is also congruent to 1 modulo p. And from here, we can infer that 2 to the power of the GCD of 2 to the m minus 2 to the m and p minus 1 is congruent to 1 modulo p. And now this is a part of this is from Fermat's little theorem, and this is just a thing that's true. If m to the power of a is congruent to m to the power of b is congruent to 1 mod p, then so is m to the GCD of a and b is also congruent to 1 modulo p. And let me actually prove this for you if you're not familiar. The proof goes like this. If this isn't always true, then take any m for some m. If this isn't true for some m and some prime, then take the smallest pair, the pair a and b, with the smallest sum over all the pairs over which this isn't true. So this is 1 modulo p, and say this isn't true. Well, what does this mean? Well, this means just p divides this, and p divides m to the b minus 1. We subtract, p divides m to the a minus b, m to the b of m to the a minus b minus 1. Let's just assume that a is greater than or equal to b. That's when we subtract. And now from here, p and m are relatively prime. So know that p divides m to the a minus b minus 1, i.e. this is congruent to 1 modulo p. And now we have a contradiction. We get a smaller pair, a minus b and b. So because we got a contradiction, like that means there's no smallest pair, which means there's no pair whatsoever, like no pair with the smallest sum. And now that that's settled, and we have this thing right here, let's take 15 minutes and try to figure out what would you do with it. Is there anything you can do with this? Here's the next step. So we got to this point and we couldn't get any further. So now let's go back to the drawing board. Let's look at this and this, minus a modulo p. Okay, so now what we have is, okay, if I take this, say n is less than m, then this to the power of 2 to the n minus 2 to the n, 2 to the n minus 2 to the n. And what we get is that this is this. We get a to the 2 to the n minus 2 to the n is congruent to negative a modulo p. Okay, so now we have something different. Now I invite you to take 5-10 minutes with this. See if you can push this forward. And the answer is, well, notice we have primes p1 through pk. And m minus n, we can assume this is less than or equal to k, or say k plus 1. I think k is actually good enough, but let's just put k plus 1 just in case. So now this sort of thing, p divides a to this plus a. And this thing right here is somewhat bounded. So this means our primes are bounded from above. But can we do better than this? Now that's the next question. And the answer is, well, where do we use the fact that p was prime? We didn't use this anywhere. We could have had p to the alpha, and still you can square these and you get p to the alpha, i.e. p to the alpha divides this. And now I invite you to take 5 minutes and see if you can finish the problem up. Well, the only thing you really need to finish up is to show that this can be as large as you want it to be. So that after some point, this p to the alpha, this sort of shared prime factor between 2m and n, can be as large as you want it to be. And now how do you prove this? Well, all these primes divide 2 to m k plus a. Two of these will share a same high prime exponent. Now, a way to think about this quickly is to think, okay, all of these are a combination of p1 to the alpha 1, p2 to the alpha 2, pk to the alpha k, and then this is, say, alpha 1m, alpha 2m, alpha km, and then this is p1, and so on and so forth. And we want one of these, for each of these, we want one of them to be greater than some, say, capital M, which we will figure out later, to get this to be impossible. So to get that, to get the maximum of alpha I for each one of these to be greater than M, then we just need to make sure, what if they're all less than or equal to M? Well, in that case, we have P1 to the alpha, Pk to the alpha K will be less than or equal to P1, P2, Pk to the power of this M. And now we just need to, this is 2 to the 2m plus t greater than or equal to 2 to the 2m plus a. And now we just need to make sure that m is large enough such that 2 to the 2m plus a is actually a lot bigger than this. Now such an m exists, we can find it and get to a solution. And here, I would invite you to pause for 10 to 20 minutes and try to connect all these ideas together and write up a solution. That's what we'll be doing next. So this is what we do. We assume the contrary. Let P1 be all the primes, P1 through Pk. They divide sum of the i's, where ai is 2 to the 2 to the I plus a. And we say let m be a number such that 2 to the m is greater than a to the power of 2 to the power of 2k plus 10 plus k squared, and all of this plus a. Just to be safe, let's have a much bigger m. And let n be a number such that 100 times p1, p2 through pk to the power of m is less than 2 to the power of 2 to the n. Actually, let's just make it 2 to the n. And let's add 64 here, just for a better bound. And then we say among these numbers, let p I1, I0, I1 like k be primes such that if 2 to the 2 n plus j plus a is p1 to the alpha 1 through pk to the alpha k, where every single alpha is greater than or equal to 0. And if the maximum of the alphas is alpha t, then let pi of j be equal to pt for every j 0 through k. And now we say, we can first do the thing where we know how big this alpha t is. So the first thing we will prove is that pt to the, actually instead of pt, let's say pit. If pit to the alpha fully divides 2 to the 2 to the n plus t plus a, if this is true, then alpha is greater than in all likelihood. Yeah, let's do greater than. Then alpha is greater than m. We assume, and the way we prove this is we assume the contrary. If not, then 2 to the 2 n plus t plus a is equal to p1 to the alpha 1 through pk to the alpha k. And then because this one is the highest one, the highest alpha among these, then all of this is less than or equal to p1, pk, and every single one of these to the power of m. And this is equal to p1 through pk to the power of m, which we know, given how we chose them, we know this is less than 2 to the n over 100 times 64, which is less than 2 to the 2 to the n plus t plus a for every single t. And this is a contradiction. And now we take this to the next page, and what we have is, so this is what we have, and now we know this to be true, then alpha is greater than m. And now we know that among these numbers we have that among pi0, pi1, pik, given every one of them is one of the primes from p1 to pk, we have L and T such that PIL is PIT, L is less than T, L is greater than or equal to 0, and T is less than or equal to K. And now with these, we know that Pi to the L to the power of M divides 2 to the power of 2 to the N plus L plus A, and P to the I, PIT to the power of M divides 2 to the 2 to the N plus T plus A. And now from here, what we conclude is, we know these two things to be true. And now, given that PIT, PIL is equal to PIT is equal to, let's call it just P, then from here, we know that P to the M divides A to the power of 2 T minus L plus A. However, the thing we know is that, just by the thing above, 2 to the power of M is greater than this. And now that we know that T minus L, this thing right here, is definitely less than K. I mean, say less than or equal to K. And now given this, we have this bound. From this divisibility, we have P to the M is less than or equal to A to the 2 T minus L plus A, which is less than or equal to A to the power of 2 to the power of K plus A. And this is strictly less than A to the power of 2K squared plus 2K plus 10 plus 8. This was an overkill. And this thing right here is what? This is less than 2 to the power of M. And this is less than or equal to P to the power of M, which is a contradiction. And now, this given our initial hypothesis led us to this contradiction, that there's a finite number of primes, led us to a contradiction. This means our initial assumption was false, and we have proved what we needed to prove. And as always, thanks for problem solving.